All right, so I'll start. Hello, everyone. I am Sahaj Sarup. I am an applications engineer at 96Boards within Linaro, and I am with
I,
here with Keith.
I'm Keith Lee. I am a software engineer at Altium, um, and we're here to talk about 96 boards, drones, and PX4. Obviously, take it away, Sahaj.
So this project was a collaboration between 96Board, PX4, and Upverter, and that's where Keith comes in. And we'll talk about that in a bit. So, what is 96 boards? 96 boards is open platform specification. It's a set of document that lays out the physical and software requirements for a few types of development platforms or development boards, and we are focused around ARM based SoCs in the consumer enterprise IoT market, and anything else that comes along with it, whether that's compute or TV networking, etc. Um, our main goal as a spec um, is to provide path to product to our partners. So suppose you buy a board that has a Qualcomm SoC on it, um, we expect our community members to buy those boards, develop something around that, and then in their final product buy Qualcomm parts in large quantity, and use that in the board. So we don't expect we are not based around um, large amount of sales. We want to provide a part to product for our stock vendors. We are very much SoC agnostic. So I gave an example of Qualcomm, but we've had boards from NXP, Rockchip, and many other vendors. So we want to give our community a large amount of choice in what sort of capabilities and functionality they want in their development platforms. Um, and also keep the form factor exactly the same. We are involved with a lot of upstreaming process in the Linux kernel, in Zephyr RTOS systems, Opti development, and other a lot of things that is mentioned on the slides. We are involved with all of them. So, in terms of specifications, we have four main specifications. We have the consumer boards. These are credit card size form factor boards with your regular desktop like SBC like IO with high speed connectivity and low speed connectivity. Um, and your regular HDMI, USB, and all that stuff. Our enterprise boards are much larger, full server size boards that are not focusing towards the cost, but more focusing towards performance and features. And then finally, we have IoT edition boards. Those are more focused towards MCUs and RTOS applications, although we have a few that actually have a Cortex A on them and run Linux, but they're still on the very power efficient side. Today we are going to focus on the SOM spec based product, and these are SOM or system on modules that you can put in your final um, product. Our SOMs are designed towards industrial grade connectors, so they can be used in high vibration or hard dust environment, and the connectivity between the SOM and the baseboard should not be affected. And um, our aim with SOM is to actually go in the final product and to benefit our community and our vendors in that manner. Again, with the SOM form factor, you get a choice of multiple vendors, multiple type of SoCs, and so our commitment towards being vendor agnostic is remains the same when it comes to our SOM spec. All right, so overview of this project, what we are showcasing here today. Early, Earlier last year, we wanted to dive into the drone ecosystem, and we thought we can try and build things from ground up, but that turned out to be a bit more difficult. So I started getting involved with the PX4 community, and at that point, we sort of attempted to reuse AeroCore 2, which was a design by Gumstix way back in the day, focused around the drone platform. But eventually, we wanted to move our design to the present generation of Pixhawk boards and platforms, and we decided to partner with PX4 and um, Upverter to do that. We are targeting PX4 FMU V5X as our FMU platform, and we want to combine that with our SOM and our um, consumer edition boards to provide a platform that has an application processor on it and a separate flight management unit. So we'll just go ahead and see how that looks like. But in terms of use cases, um, we want to distribute the workload with high performance processing being towards the application processor side, and we hope to achieve a lot of that on drone itself, so we don't have to send back data for processing, and the main flight telemetry and flight profile being handled by the FMU. And yeah, so that was our basic goals. One of the things we wanted to achieve is to try and explore as many ways to connect the PX4 FMU with our SOM and our CE baseboard, and see how well we can make both of them dance together. And so for example, in today's project, we have on board on PCB Ethernet, on PCB CAN over SPI, and we will go into details in a bit. So we decided to work with two separate form factors. We have one of them to show here today. The first one we decided to work on was a CE mezzanine. Consumer edition mezzanines are what shields are to Arduinos. These are expansion board that you can put on our consumer edition boards for expand hardware capabilities. So we wanted to use that interface to add a PX4 unit and drone interfaces to our consumer edition board. And the second one is the SOM baseboard, which we are going to show today. Is basically a baseboard that takes the FMU V5X SOM and the 96 board SOM and sandwiches them together. And it's built to be feature rich. We have tons of connectivity between the two, and even externally to the drone itself. And so let's go ahead and explore that. So this was the mezzanine design. I'm going to skip over because I'm watching the time as well. This is the SOM FMUV5X baseboard. I don't know, Keith, do you want to explain how things are connected from here?
Sure, I can take that. So the 3D render you see in here is actually generated by the Upverter tool, and you can see here that there is a connection graph showing how everything is. There's a lot going on here, so I won't go into too much detail, but it sort of explains how the different components interconnect and how the Pixhawk is talking to the 96 boards SOM. Sahaj, if you want to change slides, I'll start talking about how Upverter connects all these things together. Okay, so the advantages to Upverter over traditional PCB design is that you're using a simple drag and drop interface. If any of you attended the the 30 minutes to smart flight controller that Andrew Smith did earlier. He did a demo of putting this stuff together. So the advantage of this is that the design blocks that you drop on there are function centric. So if you need an inertial motion sensor, if it's a multi-chip pack, all those chips are going to be in there. All of the passives will be included. All you got to do is connect it to the FMU. The tool actually automates a lot of supplementary things, such as the documentation, the generation of the schematic and layout, and there's even some device tree support. Now, in the case of the RK3399 Pro, it's not there yet, but we're working on it, and it should be available in the coming months. One recent development that has made a lot of people happy is we now provide the unrouted Eagle CAD files for free through the tool. So you could potentially design the board that you want in Upverter, export the Eagle CAD files from the Upverter tool, and finish off the design and order it yourself. This also means that there's a lot more of a open source feel to the Upverter tool, because you can get those design files and work with them. One of the big things about Upverter is the fast design cycle. You're able to iterate very quickly on your design. During better days, we have like a 3-week turnover. You can order a board and have it in hand in 3 weeks and be testing it out already. Right now, of course, part procurement is a huge impediment for everybody. But the benefit is that Upverter is taking care of all that. You don't have to source your parts. You don't have to manage your BOM. We take care of manufacturing, assembly, and shipping on top of that. Okay, so Sahaj, could you advance the slide? Thank you. So in order to meet the targets put forth by the 96Boards community, we started with creating our connections from the perspective of buses. So when we wanted a header to the serial console, for example, or a UART interface, we didn't have to connect the TX and RX lines. We didn't have to worry about which was send and which one was receive. It was just adding the connection between the two parts. This goes for UART, USB, GPIO, and so on. The other thing is it's really easy. We used bridges, which would, for example, invert the UART signals so that TX from the SOM went to the RX line of the FMU, and so on and so forth. It's really easy to do things like UART over USB, or multiplexing the UART line so that you could use a single USB connection to communicate with the serial console of both the FMU and the SOM. And again, because this is all based on connecting buses, you're not focusing on how these are mechanically connected, and so it's a lot simpler for anyone to get started. So in order to expose as many I/O features as possible between the two modules, again, I talked about them being function-based modules. Well, it's also contextual. So some modules have the ability to be either I2C or SPI, and the capability of connecting either way is built into the Upverter tool. So you get to choose exactly how they're communicating. On top of that, the interface has the idea of green means go, which means as you're putting your board together, if a component if a module doesn't have the connections it needs, it'll be red. If the connections are there but they're not put together, it'll be yellow. And then once it's green, everything's in place, nothing's overlapping, and so on and so forth. There's a quick video here. Let's see if it works. Sahaj, can you make that big? Is that possible? There we go. Yeah, so this is just the process of connecting the Ethernet PHY bridge between the 96-board SOM and the PX4 module. So there's the PHY bridge, and then the transceiver, connect power, MDIO, and so on. And then it's done. That's it. Are we stuck in the video?
Okay. There you go.
Oh, perfect. Okay. So on to the next slide. So the design stage to board in hand was delayed, of course, because we could not procure the CAN FD transceivers that we were sourcing, and of course the Ethernet transceiver was also in short supply. But it kind of worked like this. Sahaj and I got on a Zoom call, and we spent 2 hours sharing screens in Upverter, just putting the parts together the way we wanted it. Once we had communicated with the rest of our team, we placed the first order. 15 days later, the first order shipped. We decided to get that one out as quickly as possible, so we left the CAN transceivers unpopulated and got it out the door. And then, of course, we went through the whole test and review process. And finally, we completed the layout on the current revision and shipped that a month later. And now Sahaj and I both have our boards in hand. Okay, go ahead. Oh yeah, so what's next? We get Auto BSB support for the 96-board SOM, and then possibly if there's a good use case for it, we add Auto BSB support for PX4. Basically, this is getting all the source files you need to get the peripherals up and running as fast as possible automatically from Upverter when you're ordering. And then, of course, comes the live demos. And these two little clips you see here. The one on the left was the AeroCore 2 live demo in my office, where I had accidentally inverted 2 of the PWM connections, and my drone went a little crazy. The one on the right was Sahaj's demo for 96Boards open hours, where clearly there was some electrical difficulties.
Yeah.
And that's it for me. Back to Sahaj.
All right. So this is the board we are talking about today. Now it looks cool in the spinning table, but let's talk a bit more in detail. So this is sort of what our layout looks like. It has changed tiny bit in the new revision, but for the most part, it's the same. On the front of the board, we have our FMUV 5X, and we have 2 Raspberry Pi cameras. One of them is hidden here. And moving down, we have our 8X PWM header. In the current configuration, I think one of them is used as the input for the radio. And then from there, we have our telemetry, GPS, RC input, our CAN bus, and HDMI. HDMI was just one of those things that, why would you need HDMI on a drone? In that edge case where you need an actual display on the drone to go ahead and show things to people, or like configure drone on board, or but for me it was mostly to like debug and work on the board itself, instead of having to SSH or have just a command line utility working. Since my primary, um, the MVP demo included some video footage, and having the camera working to see that video output, it was kind of necessary. So it's more of a debug thing, but it's fun to have HDMI on a drone. Why wouldn't you if you can? And then we have USB 3 Type C. It can be used as power input for all the digital logic, and but it can also be used as a USB 3 hub for your high speed camera interfaces. That's what the primary goal here is. A 2S battery connector, but I think it can go up to like 16.5 volts. You can probably add a 3S battery without the balance leads. um, and then we have a micro B connector. Now this is a fun one because it extends onto a USB hub, and then you can get two UARTs. One of the UART goes into V5X debug, which you can use to connect to ground control externally, and the other one goes to the 96 port SOM. And then an M.2 key. There are some LTE modems for M.2 key, but which I know a lot of people in the drone community want LTE on their drones. But for my use case, I just wanted a very high speed storage to store any incoming 4K footage, or directly on the drone, and not have it transmit on in a lower quality. So having an onboard storage for nice shots, that's fast enough is a plus. This is the backside of the board. You just have your SOM and other supporting logic, but yeah, the main part is the 96 board SOM that stays at the back. Right, so I will quickly move into the demo because we have less than 10 minutes. All right, quick demo. I will switch my camera, and hopefully now my face comes up. What's going on? Uh,
Lens cap.
no, this is my OBS camera, and it's not letting me click apply. This is weird. Let me try completely disconnecting my camera. So it has to force. No, it does not. Uh, we ran through this before the demo. Okay, now I cannot select any camera. All right, so in the interest of folks, we have a backup demo pre-recorded. I just have to talk over it. I'm not sure what's going on my end, so we'll just run the backup demo, which means you won't be able to sadly see the new board. We had the demo running on the new board. Now this is a setup. The FMU board looks is electrically same to this particular setup. I have my SSD on this card here. My board is here, and the FMU is on a separate board connected over UART. I just wanted to show the functionality and what sort of what we are going through. It's an NVP demo showing the connection between the SOM and the FMU over Mavlink. This can be done over Ethernet. The on board Ethernet we have on the actual board itself, or over UART, which also is on the board, and then CAN bus and I2C, I guess. But on this particular demo, it is running on it's running on UART. Right. So the initial bit of the demo is I'm just running a program that records a video on the USB cam and overlays some information from the FMU, and which is updated live. So if I'll go ahead and quickly play that back. As you can see a few information from the FMU. You can see the firmware version. You can see the status. It's not armed. It's on standby. And as I move the FMU around, the heading changes. So it's grabbing live information from using Mavlink onto the FMU. So that was a sort of minimal MVP demo of the two things working together. Of course, that's not the only possibility here. Um, and as the months go by, when I get the opportunity to put that code onto an actual drone, these demo will be made a bit more complicated and improved upon. So quickly, I want to go through the code. It's something that is very simple. If you don't want to manually deal with Mavlink, Python library, which can be a bit overwhelming because you have to do a lot of manual setting up of strings and then passing them. You can just use a library called Drone Kit. It's a wrapper around Mavlink. It does all of the complex stuff for you. You create a vehicle variable, just connect to it. You can connect over IP or you can connect over serial. Both are fine. And then you have simple function in there. So vehicle.version gives you the firmware version, and similarly system status and vehicle heading and many more. So you can pretty much get whatever Mavlink can send you through this library. We are using kind of a hack to overlay the text right now, and the hack is to write the text onto a file. So we have a buffer here which has all the text that you saw on the video, and it updates every second, and we write that to a particular file, and we then tell FFmpeg to draw text using the text on that file, so it updates every second on the actual video stream. So that was a quick demo, and we have a minute to spare, so we'd appreciate it.
There's just one question I wanted to address before we close.
Yeah.
Thanks, Brent, for asking. With a lot of the high-speed signals, I understand your concern wanting to make sure there's enough room for routing. A lot of the high-speed signals, you'll find that there is a path that extends from where it's the source of the connection to the sink, and it'll indicate in green if there's clearance, or if it's within the constraints of the signal, or it'll come up as red if it's blocked or if it's too far away from the source. That is one way we handle high speed. Another way is we manage all we verify routing before we ship. So one of our electrical engineers reviews every design and makes sure that every signal is routed and follows the constraints that are defined by their specification. So it's generally it's handled, is what I'm saying. Is you'll know that your design is valid. And that brings us to time, I think. Well, thank you very much for joining us.
Thank you, everyone, and I hope you all enjoyed the presentation.